Electric fields. A field is a region where objects with particular properties experience a force. A gravitational field, for instance, is a region where objects with mass experience a force. An electric field is a region where objects with charge experience a force. In a uniform electric field, charged particles will experience the same force and therefore the same acceleration wherever they are within the field. A uniform field can be produced by applying a potential difference to two parallel metal plates. So here we have two metal plates connected to a potential difference, with the bottom plate being positive, the top being negative. If we placed a positive charge here, it would feel a force towards the negative plate. If we place the charge here, it would experience the same force in the same direction. Also here, the field is uniform between the plates. We can represent the field with field lines, rather like you're used to for magnetic fields. The field lines would go something like this. The relative density of the field lines shows the field strength at that point. As this is a uniform field, the field lines have uniform density in the space between the plates. The direction of the field lines, in this case upwards, shows the direction of the force on a positive charge. In reality, this field would be slightly weaker at the edges of the plates, as shown by these end field lines bowing outwards. Electric field strength is defined as the force per unit charge, which we can write as E is equal to F over Q, where E is the electric field strength, which will be in newtons per coulomb, as F is the force in newtons, and Q the charge in coulombs. For a uniform electric field, the electric field strength is equal to the potential difference divided by the distance between the plates, which we can write as E is equal to V over D, where V is the potential difference in volts, and D the separation of the plates in meters. This shows electric field strength can have alternative units of volts per meter. The different units can be useful in answering problems, because there are two different ways of thinking about an electric field. For example, two long parallel plates 5 centimeters apart have a potential difference of 2.5 kilovolts between them. Calculate the electric field between the plates. Well, for this we need the formula electric field strength is potential difference over separation, which, putting the numbers in, gives an electric field strength of 50,000 volts per meter. And the volts per meter makes sense in terms of a potential difference across a distance. Next, we're asked to calculate the force exerted on a proton between the plates. For this, we need the formula electric field strength is force over charge, which we can rearrange as force is equal to electric field strength times charge. Putting in the numbers gives a force of 8 times 10 to the minus 15 newtons. In this case, I've used the units of newtons per coulomb, as we're looking at the force per coulomb of charge.